Having learnt the various aspects to be considered in the design of beams in the previous class, like the bending moment consideration, shear force consideration, deflection consideration, we now take off with a simple problem in the present class of design of beams part 3. Are you ready with your steel tables, calculator and all? Yes. Here is a problem for you. Please note down the problem. A simply supported beam carries a superimposed load of 35 kilonewtons per meter run on an effective span of 4.5 meters. Is that right? A simply supported beam carries a superimposed load of 35 kilonewtons per meter run on an effective span of 4.5 meters. Now calculate the total load on the beam, bending moment and shear stress, followed by section modulus required for the beam. So you are required to calculate the total load, bending moment, shear force and the corresponding shear stress and the section modulus required for the beam. Design the beam also. Now, the permissible bending and shear stresses may be taken as 165 and 100 newtons per mm square respectively. Assume the beam to be laterally restrained. I have explained to you in the previous class about the lateral restraint, is it not? When the compression flange is held in the slab, when the compression flange of the beam is held tightly in the slab and it is not allowed to move from its position, then the beam is said to be laterally restrained. This is the simplest case, and when you are not given about the lateral restraint, you have to assume preferably that the beam is laterally restrained, right? And now tell me what you are going to do as soon as you are given this problem. First of all, you have to calculate the loads. In the second stage, calculate the bending moment. And the third stage, you choose a section which is slightly having a section modulus greater than the required section modulus. That is the third stage. And in the next stage, we check whether the section that we have chosen is safe with respect to deflection and with respect to the shear stress, etc. So shall we move on to the solution part? Here is the solution. When the beam is laterally restrained, sigma BC is equal to 0.66 Fy, where Fy is the yield stress of steel in newtons per mm square. In case you are using the mild steel, then the value of Fy will be 250 newtons per mm square. In case you are using steel of any other grade, you have to take the yield stress of the corresponding grade. So now here, since sigma BC is equal to 0.66 into 250, that comes to 165 newtons per mm square, which is already given in the problem itself. And now you see, we are here to calculate the total load which is coming onto the section. Now the superimposed load is given to be 35 kilonewtons per meter on an effective span of 4.5 meters. Now any member you choose will have its own self weight, right? And that self weight is WL by 300. W is given as 35 kilonewtons per meter, right? This is the UDL which is given here, into the span is 4.5, this is 300, this comes to 0.525 kilonewtons per meter approximately. whatever section we choose, probably this may be slightly higher or lesser than this value. Now the total load comes to, what is the total load here? It is the superimposed load plus the load per meter run because of the self weight of the beam. This comes to 35.525 kilonewtons per meter, and this finishes the load calculation. What is the next step that we are going to do? We are going to calculate the bending moment, right? And now, what is the maximum bending moment on a simply supported beam? It is WL square by 8, where W is your UDL, right, or the load per meter run. This into 4.5 is the span square by 8. This comes to, you please make a correction, it is kilonewton meter, not per meter, 89.92 kilonewton meter. This is your maximum bending moment which is occurring because of the load, because of the superimposed load and the self weight. This is the maximum bending moment which is occurring. And now, according to the bending moment you have calculated, you have to make an estimate of the section modulus required. How do you get that? That is the bending moment divided by the allowable stress. Which sort of stress is it? Bending compressive stress. That is sigma BC, or you can call it F also. This we have calculated earlier as 89.92 into 10 power 6. This is estimated to be 165 because the beam is laterally restrained. We have taken the value of sigma BC or F as 0.66 Fy. That comes to 165 newtons per mm square. Now what if the beam is not restrained? Not restrained in the sense there is no support given to it. The compression flange is not supported in any way. Then what are we to do? This permissible stress will be slightly lesser. Is it clear? When the beam is not laterally restrained, this value is not 0.66 Fy. It is slightly lesser, and that has to be calculated from the IS 800, IS code 800. The tables 6.1, 6.2, you find, you can get the values of sigma BC based on D by T and L by Ry values. That is a slight modification of the problem. You can try it later on. You can try the same problem wherein the beam is not restrained. Then you have to pick up this value from the IS code. Now this is your section modulus required. What are we to do now? You have to choose a section which has section modulus slightly greater than this. It should not be abnormally high. It should be slightly greater than this. Now we move on. Shall we choose a section? Take out your steel tables. Now here, I think this would be adequate. Let us provide ISMB 300. This is the self weight, right? And the section modulus of this section is 573. I'm sorry, 5,73,000, so much mm cube. This is slightly greater than what is required. Now what should we do? We have to check the section. You have to see whether it is safe or not. Now what is the first check that we make? Yes, it is the check for shear. The maximum shear force is to be calculated first, that is WL by 2. W you have already calculated, it is 35 plus 0.525 UDL plus self weight, is it not? But the section we have chosen, if you observe, has a self weight slightly lesser than this. So we are on the higher side. You have taken the self weight slightly high. Fine. So this is your total load into span by 2. This is the shear force. It is 79.93 kilonewtons. And now because of the shear force, we have to estimate the shear stress that would be developed. Is it clear? We have calculated the shear force, and because of that shear force, let us estimate the shear stress which is resulting. That comes to you because I remember I have told you that the shear is entirely borne by the web. The web has a depth. This is the depth of the web. This is the thickness of the web. Clear? So, this portion, the portion of the web is taking the shear. So, actually what is the stress equal to? Load by area. Here you are taking the cross sectional area of the web. Now, S divided by D into TW, this comes to 35.52 newtons per mm square. And now, what is the permissible shear stress? It is 0.4 Fy. Fy is again 250. This comes to 100 newtons per mm square. This is fairly less. So, with respect to the shear, the section we have chosen is safe. What is the next that we are going to do? You have to check for deflection. And what is the maximum permissible deflection? It is L divided by 325. That comes to 13.8 mm. L divided by 325 in mm, it has come to 13.8 mm. So, what is the actual deflection? How do we calculate the actual deflection? See here, the actual maximum deflection in the case of a beam carrying uniformly distributed load is 5 by 384 W L cube by EI. In case this is the total load, here as I have told you, you take it as capital W. In case you take it as load per meter run, it will be small w into L power 4. Here this W indicates the total load of the beam. Fine. And now how much does this come to? It is very less, 2.44 mm. So, absolutely safe. Is it not? So, with this, I am confident that you are able to design a very simple beam. Simple beam in the sense, you can choose a section from your steel tables, either I section or channel, whatever section is appropriate you feel, you can choose it from the steel tables. Now, how about sections which have to support much higher loads? What should we do? You can observe from your steel tables that the I sections are restricted in their depths. That means you don't find sections of abnormally deep, abnormal depth. Maximum I think you can find up to 600 mm. And now what if you need a section which requires to support much higher loads, longer spans? What should we do? What do you do to increase your strength? You go in for bodybuilding, is it not? In the same way, these simple beams can be strengthened. How? We will see in the topic to be followed. And such beams are called built-up beams. Shall I move into the topic? Yes. What are built-up beams? In simple terms, you can say that built-up beams are stronger beams. That means they have a lot of strength to support much higher loads. They offer, this is more technical, is it not? They offer more section modulus. That means they can resist more bending moment. Directly to say they support higher loads. And now, how are they made? How are built-up beams made? By increasing the strength of rolled steel sections by adding plates to the section. So, there is another name for this built-up beam, that is, you can call it a plated beam. Take an I section, add plates to it, it becomes a built-up beam. So, the other option is by compounding a number of rolled steel sections. What are the various rolled steel sections that you know? Can you name some? I sections, channels, these are the available rolled steel sections. You compound a number of rolled steel sections. That means you are choosing sections in multiples. You take 2 sections or 3 sections so that the entire compounded section will be able to support the large loads. So when do we opt for built up beams? I have told you, when the section modulus is more. A single section cannot support the required or it cannot offer the required section modulus. Then we opt for built up beams. And when the depth is restricted, wonderful. This is a very important term I have been stressing on since the beginning of the topic. The depth is restricted. I told you the web supports or the web takes the shear. As the shear force is increased, you have to keep on increasing the depth of the section. Whereas in case of simple beams, you cannot increase the depth infinitely because rolled steel sections are prefabricated. So when rolled steel sections are inadequate, in the sense section modulus is more or the depth is restricted, then we opt for built up beams. And will you see some different built up beams? Here they are. Here we have an I section, okay, and the plates are added to it. One plate on this side, one plate on this side. So you have a rolled steel section, I section and plates on either side. So such a beam is called a built up beam, a plated beam, or you can also call it a compound beam. And how about this? See? And if your load is much more, if the load is much more, a single plate is not sufficient, then take an I section, add 2 plates on either side. These plates offer some section modulus, I section offers a part of it. So this completes or this gives you enough section modulus. Yes. Now take a look at this. Here you see a single I section with plates is not sufficient. Then you can choose 2 I sections placed side by side and join them with the help of plates. Joining in the sense, in the next class we will be dealing with the riveted joints. There we will see how to design a riveted joint. Here you can have rivets like this, or you can also go in for welding. Now see this, you need more depth. You have an I section over an I section. So this is a compound beam. Look at this, I section, plate on one side and a channel on the top. Is it not? At this juncture, I would like to tell you the built up beams are in some cases symmetrical, in some cases unsymmetrical. This is a typical unsymmetrical section, right? I have been telling you about the symmetry. The more symmetrical the section is, the more stable it is. But still sometimes when a channel and an I section are available for you, then you may have to opt for this. Look at this. This is a channel, this is another channel, right? So these are the various possible types of sections that we can choose in case we opt for a built up beam. And now what if a built up beam is also not sufficient? The shear forces are very large, then you need a section of much more depth. Then what should we do? Yes, the topic that is going to be followed will tell you about all that. The choice of a beam section. In the first class and second class, I told you about the simple beams. And now just before I taught you about the built up beams, and next follows the plate girders. Like, it is a stepwise procedure for increase in load and span. The much higher the load is and the much more the span is, then you have to go in a, you have to rule out. Simple beam is not sufficient, a built up beam is not sufficient, then go in for a plate girder. So what is so great about a plate girder? Its depth is very large. It has a deeper section. The web plate will be deeper, and there you don't have any prefabricated or rolled steel sections are not used. The main sections are also plates there. Now see here, a plate girder. What is a plate girder? Plate girders are deep structural members. Yes. How deep? I shall tell you soon. Just note down, they are deep structural members. That is, the depth of the section is very much high. Just as in any other case, in the case of simple beam or a built up beam, just as the loads are transverse, even here the loads are transverse. That means the loading is in a direction perpendicular to the neutral axis. That is meant by a transverse load. It consists of plates and angles riveted together, or in some cases they can also be welded. In case the section is, or in case the plates are riveted together, it is called a riveted plate girder, and in case they are welded together, that is called a welded plate girder. More points? See here. Abnormally high. See, the plate girders are used for spans up to 100 meters. Wonderful, is it not? Such large spans they use plate girders. Depth is about 5 meters or more. In particularly in case of very heavy loads, the depth you can take up to 5 meters or even more. But under normal conditions, the depth of 1.5 to 2 meters is common, right? See this? This is a plate girder. What is the difference between the previous built up section and this one? There you had an I section, rolled steel section we have used, but here there is no rolled steel section. You have a vertical member. Can you just make a guess about it? What is this member called? Web plate. This member is called a web plate. You have 4 angles. Ultimately, it takes the shape of an eye, but it is not a rolled steel section. You have a plate and some angles. You want to see another one? See here? Yes. You need a section which offers more section modulus. Take a web plate. What are these plates called? Flange plates. These angles are flange angles. If you observe it keenly, you can find a gap here. Just guess, why should you have a gap here? You have a gap here. You have a gap here and you have a gap here. That gives you a provision for expansion and contraction of the web plate. This is made of steel, so obviously there is a chance for expansion and contraction. So this gap provides you with that. So you have a web plate, one flange plate on the top, one flange plate at the bottom, and 4 angles. Now to the next one. Yeah. See, this section will obviously offer much more section modulus, or it can resist more bending moment. That means it can resist more loads, much heavier loads. See here, there is a web plate. There are 2 plates 2 plates at the top, 2 plates at the bottom, 4 flange angles, and these plates are the filler plates or packing plates, you can call them. And the sections can be riveted. You can have a rivet here, one rivet on this. That means rivets connecting the flange angles to the web plate, flange angles to the flange plates. So these designs you can learn later on, and at this point let me tell you something more about the flange plate also. These flange plates can be curtailed. Curtailed ante? Curtailed in the sense they can be cut down. When you have a long span, the bending moment will be more at the center of the section. So you can have the plate there. As you look to the supports, as we look at the bending moment diagram towards the supports, the bending moment decreases. So this plate, the top plate, may be cut down at some extent. You can have the piece wherever it is required, and you can cut it down or you can curtail it wherever it is not required. That is called curtailment. Look at this section. You have 2 web plates here. One web plate here, another web plate here, 2 flange plates, 4 angles. So why do you need 2 web plates here? Web plates take the shear, is it not? Web plates take the shear. So when the shear force is more, then you need more area of the web plate. In such a case you can go in for 2 web plates. In such a case it is called a box girder. It is called a box girder. Now I think you are in a position to tell me the various components of a plate girder. The central portion is the web plate, right? We have the flange plates on the top. I shall explain to you about the various components in detail also. I am just trying to list out the components of a plate girder. The first one is the web plate. At the top and bottom you have flange plates. We have flange angles. Here we come across a new term, web splice. I shall tell you what a splice is. We have flange splice, vertical stiffeners. You can write down horizontal stiffeners and bearing stiffeners. We shall now discuss about the various components in detail. What is the first one? Web plate. And before I take up the web plate, you see here we also need riveted connections. I told you we have to connect the flange angle to the web plate, the flange angle to the flange plates. So these are the riveted connections which are also to be designed. Now this is a typical plate girder. See, this is the 3-dimensional view. Please try to identify. This is the web plate. It runs across, the web plate has to run across the span. This is the span. The span may be about 100 meters also, right? This is the span. So this web plate will run along the span. This is the flange plate, the plate on the top. This also runs along the span. See, from here it goes on till the end of the span. This is the bottom flange plate, which has also to run along the span. If the span is 50 meters, the span or the length of this plate will also be 15 meters. In the similar way, the length of this plate, web plate, must also be 50 meters. See, this is the flange angle. There is another flange angle on the other side, right? Here on the top, this is another flange angle. The other side, another flange angle. Now what is this? What is this? This is a stiffener. Have you ever seen a fence around the house? You just plant some small plants around and you try to make them straight. Then what do? We use some additional members, horizontal members and vertical members to put them in position. So this is a stiffener. The name itself suggests it tries to stiffen the web plate. Now just imagine what happens to this web plate if it is very deep, as deep as 3 meters or 4 meters. If this is very deep, what happens? It needs some additional support, right? And that support is offered by this stiffener. A stiffener is an angle which supports or which offers additional strength to the web plate. This web plate may buckle, it may bend down. It prevents from such a thing to happen. We can also have a stiffener in the vertical direction. The same stiffener which is in the horizontal direction can be placed vertically, right? We didn't have it in this diagram because it may be confusing. This same member, you put it in a vertical direction, it becomes a vertical stiffener. So this horizontal stiffener, and if at all we have another member like this, a vertical stiffener, these are called intermediate stiffeners. I will repeat it for you. A horizontal stiffener like this, or a vertical stiffener, the same angle placed in a vertical direction, these are called intermediate stiffeners. I think this 3D view will give you a better understanding of the various components of the plate girder. A web plate, flange plate, you can have any number of plates. You can have another plate over this depending upon the section modulus which is required. These angles, flange angles, this is the stiffener. Now, what is a web plate? What does it do? At any section, the web plate resists the shear, and there is a gap of 5 mm between the web and flange plates. Is it clear for you? Please note down these points. At any section, the web plate resists the shear, and there is a gap of 5 mm between the web and flange plates. I have explained to you the need for this gap. What is the need for this gap? This gap of 5 mm, what does it do? How does it help? It helps in providing for the expansion and contraction of a web plate. Now, what does the flange plate do? The flange plate at the top. The bending moment is resisted by the flange plate, flange angles and a portion of the web plate. Carefully observe, the bending moment is resisted by the flange plate. We also have flange angles at the top and bottom, that is in the compression zone and in the tension zone. We have, in the figure you have seen, we have 2 angles at the top, that is in the compression zone, 2 angles at the bottom in the tension zone. So these angles also contribute to the bending moment. That means these also offer some resistance to the bending moment, and a portion of the web plate also resists the bending moment. If you remember, in the previous class you have seen the distribution of bending stress across the section. A little bending stress is also there, also taken by the web plate. So the flange plate, flange angles and a portion of the web plate together, all these three together will resist the bending moment. Now what next? Flange angles. What is the main purpose of this flange angles? We have seen just now, they take some bending moment, that is fine. In addition to that, what is their duty? They keep the flange plates and web plate in their position. That means they do not allow them to keep out of place, they hold them in position. So the angles connect the web and the flange plates. So the web plate, there are two connections. If you remember well, I have been telling you about the riveted connections, or you can have a welded connection. In this connection, what do? You connect the flange plate and angle and the web plate and angle. By making these two connections, all the members will be in their position. They do not move out of place. That is the purpose of a flange angle. The first important thing is they take some bending moment. The second important thing is they keep the members in their respective positions. And like, what is the area when you design? You have to have in your mind the area of flange angles to be provided. The area of flange angles should not be less than 1/3 of the area of the flange. When we make a design, it's a trial and error method. Trial and error means we choose a section, check whether it is safe or not. If it is not safe, we choose a second member, you change, or you provide a better section. That is called a trial and error method. So initially when we choose some flange angles, the area of the flange angles should not be less than 1/3 of the area of the flange. It means it should not be less than this, it can be more, it can be slightly more. So you start somewhere here, you start with a flange angle of about 1/3 area. If it is not sufficient, go in for a angle of slightly more area. Now, splicing is a wonderful aspect. What is a splice? I have shown you in the figure and I have been telling you the web plate runs along the span. If the span is 50 meters, the web plate has to be 50 meters long. Can you get a web plate? It may not be practically possible to make a plate so long, and it is not necessary also. It may also be difficult for us to transport such a long plate from one place to another. So what do? Suppose you have a span of 15 meters and you have a web plate of only 10 meters. What do? You take two plates, one of 10 meters length, another of 5 meters length, join them. That joining of plates is called a splice, or it is called splicing. So a splice is a small plate. What does it do? Suppose I have two plates, this is one web plate, this is another, I am joining both of them. So what do? At this particular joint, I add a splice, I add another member, one member from this side, another member from this side. That small member which is used at the joints is called a splice. Splice is a small plate. See here, this is a web splice. Okay, this is the web plate, and you are joining or you are making a web plate out of two plates. Suppose this web plate is made up of two plates. I have shown you like this. This is one web plate, this is one web plate. Then what should we do? You use additional members here. This is one member, this is a small plate, this is another small plate, which is used at the joint, at the place where the joint is made. And please note, this joint should not be made at sections of severely high stresses. For example, or to be more specific, suppose the shear stress is very high at a particular point. You can't make a joint there at that point. We have to search for a section where the stress is less, and at such a point we make the joint using these small plates. These are called splices, and because these splices are used for web plates, it is called a web splice. And can you tell me another place where a joint may be required? Yes, the flange plates. If the span is 15 meters, you need flange plates of that length. You need flange plates of 15 meters length. We may not get them. So you can make a joint in the flange also. You can make a joint in the flange also. How? By using these splices, using the splice plates. And such a case it is called a flange splice. The small plates which are used for making a joint or making a joint very secure, safe, is called a splice. And when the splice is used for joining a web plate, it is called a web splice. If a joint is made in the flange plate, the splice used there is called a flange splice. And these splices can also be in pieces. Instead of a single piece, we can have 3 pieces. Wonderful, is it not? In addition to its main function of joining the plates, it can also contribute to resisting the bending moment and shear stress. So, in such a case, you can make this piece into 3 pieces. Here we have one piece, here another piece, in the center one piece. The central piece will take shear, the piece at the top and bottom will take, or it will resist bending moment. Okay? You can make a point of this. When do we opt for web splicing? When the length of the web plate is more than that available, 2 plates are joined together. Fine? And now splice plates are provided on both sides of the web plate. Now take down this point also. A web splice should resist the shear force and the bending moment at the spliced section in the riveted plate girders. In addition to its main property of making the joint safe and secure, it should also resist the shear force and the bending moment at the spliced section. Spliced section means the section at which the joint is made. There the shear force and bending moment is also resisted. And now you know about the flange splice. When the span of the plate girder is large, then the flange plates and angles are joined together to form a flange splice. Now, shall we see what a stiffener is? a stiffener is required to support or to strengthen the web plate. You can make a note here, it has buckled. When the depth of section is abnormally large, or when the depth is more, there is a tendency for the web plate to buckle, and in such a case we need a stiffener. So you have seen the horizontal stiffener in the figure. So stiffeners can be provided either vertically or horizontally. If the stiffener is provided in a vertical direction, it is called a vertical stiffener, and in case it is provided horizontally, it is called a horizontal stiffener. And with this we come to the end of the design of beams part 3, wherein you have learnt about the design of a simple beam, the necessity of opting for a built-up beam, and the need for plate girders, the various components of a plate girder. This completes the design of beams.